which both the load and the source side are complex in nature, or both the impedances are complex. We have a circuit over here. In this circuit we can see that there is an antenna, which is our load, and a transmitter, which is our source. ZT is the impedance of the source and ZA is the impedance of our load. The values of ZT and ZA is mentioned over here, and we have taken our Z0 to be 75. So before proceeding to the step, there are a few points that we should keep in mind. Point number 1 is, it is preferred that you move on your Smith chart from the side having the larger resistive value. On this circuit we can see that TZ is having a larger resistive value, so it is preferred that we should move from a side of source to the load. Well, this is not compulsory. You can either move from your load to your source, but these are few points. If you keep in mind, it will be easier for you to get done with any of your question. So in this case here we will be moving from TZ to TA. What is the second point that we should keep in mind? It is the impedance of the side, either the load or source having larger value is kept the same. The other side impedance will be taken as a conjugate of its own. Over here in our circuit, TZ is a larger side, so this impedance will be kept the same, but the impedance of TA, which is load side, will be altered, so it will be taken as a conjugate of its own. I am representing MA is equals to MZ MA conjugate, which will be having a value of 75 minus J15 for load. So we will be using these two impedances. Let me set it down. These two impedances will be using these two. Okay, what is our third point? We always move in the upper part for inductor and lower part for capacitor. Always. This is a very basic point, but it should be kept in mind that for inductor we always move in an upper plane, and for capacitor we always move in a downward plane of our Smith chart. Let's move on to our Smith chart. Before moving on to Smith chart, we should normalize these two load and source impedances. Now let's write down the normalized form. TZ the value, we're going to plot these two normalized value on our Smith chart. So let's move on to Smith chart, keeping in mind our values. Okay, here we are on the Smith chart. First we will plot TZ. Here we have a circle of 2, R is equals to 2, and we have to plot on 2 plus 1j. 2 plus 1j, 1 is coming from here, it goes over here. So this point is our you could say T point. Our second point was 1 minus 0.2. We have to plot this 1 minus 0.2. 1 minus 0.2, 0.2 would be coming somewhere from 1 minus 0.2 over here. This is the point for 1 minus 0.2. This is our Z is the M point. We have pointed all these 2 points on Smith chart. Now we'll move according to our diagram. If we see our diagram, okay, let me just set it minimum. Okay, this is much better. Now if we see a diagram and we are moving from our transmitter side, we see that we have a capacitor in parallel with the transmitting impedance. This means that we will have to move on our white circle, not Z circle. The circle will be, I will mention that circle with dark green. So it's capacitor which is in parallel. So from that T I will be moving on this plane, and I'm moving on the downward side because it is capacitor connected in parallel. This will be my direction, this will be my direction. Now when we move on, when we reach the capacitor, we see that there is an inductor which is in series. So because it is in series, we will be moving on our normal Z impedance circle, and we will be moving on upward direction because it is inductor we have approached. So I will be using dark green color this time for showing you the direction of movement towards the inductor. So I am moving towards the inductor, and here I reach. This is my inductor direction. The point where these two circles meet is our desired point over here. These are desired point. Let's name this point ZTC. Let's just name it this. We'll have to find out this value of ZTC. We'll just see what's the value of ZTC. So we have a new impedance ZTC, and we see that the value of ZTC is 1 minus 1.22J. It's 1.22J, almost 1.22J. If you go downward from there, 1.22J is almost like 1.23J. It's 1.22J, and what will be the its YTC will be? YTC will be what will be the circle of YTC? Let's see for that. It's the circle of 0.4. It's 0.4, which is just got hidden, but it's 0.4, and plus 0.2J. Now there should be a question in your mind. There might be a question why there is negative and why there is positive. Well, let's see why there is negative first. Why ZTC has a negative sign? We were moving from our point of ZT. We were moving downward because there was a capacitor, and over here at this point we reached this point which was located on the lower plane of our Smith chart. Because this point, our desired point, is located on the lower plane of our Smith chart, the ZTC will be having a negative impedance because it's ZTC, and we know that for Z the downward side is negative and the upward side is positive. The opposite will happen for the white chart. For white chart, this is negative side, and for white plane this is positive. Right now we are only concerned with a Z1, so we don't need this. That's why we have a negative sign over here. And why VTC is positive? Because YTC is 180 degree shift of YZT. That's why it's a positive sign over here. Now what? How we are going to get the value of our inductor and capacitor? So for getting a value for an inductor, we move from path of ZT to ZTC. This path will give us the value of inductor. This path will give us the value of capacitor. Because this will give us the value of capacitor, because from ZT to this point we are having a capacitor. We are reaching the capacitor first, and the second path will give us the value of inductor. Now how? But it's very simple. For getting the value of capacitor, we will subtract ZTC from ZT. But keep in mind, because we are on a circle of white circle, we will be using the value of YTC and yt. So getting the value of capacitor, we will be doing ytc subtract yt. Now let's move on to notepad. If you find on a Smith chart the value of yt, it will be equal to 0.4 minus 0.2j, and we already know the value of ytc. So how this will work? Let's move on to our notepad. We said for capacitor it will be ytc minus yt. So for capacitor we have ytc is equals to 0.4 plus 0.5 j which will give us a value of 0.7 j. Well, this is not a value of capacitor, rather it is called B, which is the inverse of our impedance. So this is 0.7 j. For Xc it will be equals to 1 over 0.7. Keep in mind that we have normalized our values in the beginning with 75. So over here we have to regain that value. We'll multiply 75 again for getting the original value. So 1 divided by 0.7, this whole thing will get multiplied, oh my god, by 75. Capacitor value, because we know that Xc is equal to 1 over 2 pi c blah 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 blah. From here the capacitor value. For inductor, what we gonna do for inductor? Let's move on the Smith chart. What will be the value for inductor? Inductor, we see that our path is this, so we will be subtracting, and we are moving on. Keep in mind that we are moving on our zth circle. Okay, so we will be subtracting z value from another z value. So here we see that it will be zm minus ztc. Simple as this. So just moving on to this, which is blah blah blah. This will be equal to, for inductor, zm minus z, oh my god, ztc. For inductor, we know our zm was equals to this. It is not our inductor value, rather it is our XL. It is XL because we were working on Z plane. In Z plane this is XL. In Y plane this value could be B. So we know that this is 0.2. We know that it's equal to 2 pi f L equals to 1.02, and from here you can easily find L. It will be equals to, oh wait, before proceeding further you have to multiply this value by your normalizing factor, which was 75 in this case. So man, bullshit. Oh, what the hell. Okay, just this is exponent. Okay, just keep in mind this is exponent, this is giga, or I just can write it giga. Multiply by my god, nothing. This will give us the value of inductor, which will be equal to 74 by 2 giga Oh, voila, we are getting a correct value. Micro Henry. Ta-da! Here are the values that we needed. Finally, we have solved this complex circuitry. Next time we'll do another circuit just for practice. For now, that's it. Bye.